Chapter 5 Electronic Structure and Periodic Trends. When sunlight passes through a prism of raindrops, the light bends at different angles and separates into the many colors you see as a rainbow. Similar colors are also seen when certain elements are heated. You see this effect during a fireworks display. Lithium and strontium make red colors in fireworks. Sodium gives yellow. Magnesium is used for white. Barium makes a green color, copper blue, and mixtures of strontium and copper make purple. This energy emitted from an atom such as visible light is a tool that scientists use to probe the behavior of electrons in atoms. Eventually, work done by physicists and chemists revealed that electrons both behave as particles and light waves. We'll also learn that electrons are arranged in different energy levels within atoms. The electrons at the highest energy level, called the valence electrons, relate groups of elements and determine similarities in their physical and chemical behavior. Section 5.1 Electromagnetic Radiation. When we listen to the radio or use a microwave oven or turn on the light or see colors of a rainbow or have an X-ray taken, we're experiencing various forms of electromagnetic radiation. All of these types of electromagnetic radiation, including light, consist of particles that move as waves of energy. Wavelength and frequency. You're probably familiar with the actions of the wave in the ocean. If you're at the beach, you might notice that the water of each wave rises and falls as the wave comes to the shore. The highest point on the wave is called the crest, where the lowest point is called a trough. On a calm day, there might be long distances between crests and troughs. However, if there is a storm with lots of energy, the crests and troughs might be much closer together. The waves of electromagnetic radiation also have crests and troughs. The wavelength, symbol lambda, is the distance from a crest or a trough to the wave of the next crest or trough. In some types of radiation, the crests and troughs are far apart, while in others, they're close together. Red light is farther apart, blue light is closer together. The frequency, symbol nu, is the number of times that the crests of the wave pass a point in 1 second. The frequency is measured in hertz, which is equal to cycles per second, or seconds to the -1. All electromagnetic radiation travels at the speed of light, c, which is 3 × 10⁸ meters per second. Mathematically, the wave equation expresses the relationship of the speed of light to wavelength and frequency. C equals lambda nu. The speed of light is 3 × 10⁸ equals the wavelength of the radiation, lambda, times its frequency, nu. The speed of light is about 8 million times faster than the speed of sound, which is the reason we see lightning before we hear thunders during a storm. Electromagnetic spectrum. The electromagnetic spectrum is the arrangement of different types of electromagnetic radiation from its longest wavelength to its shortest wavelength, or from lowest energy to highest energy. The wave equation for the speed of light, c, shows the relationship of wavelength, lambda, and frequency, nu, is inversely proportional. C, speed of light, equals wavelength times frequency, lambda nu. As the wavelength decreases, the frequency increases, or as the wavelength increases, the frequency decreases. Because the speed of light is constant, we can solve the wave equation to calculate the wavelength or frequency if we know the value of the other. To solve the equation algebraically for frequency nu, we divide each side by the equation by the wavelength lambda, and we end up with nu equals the speed of light divided by the wavelength. To solve the wave equation algebraically for the wavelength, we divide each side of the equation by the frequency nu and get lambda equals speed of light divided by nu. Scientists have shown that the energy is proportional to frequency, which means that energy is also inversely proportional to the wavelength. Thus, as the wavelength of radiation increases, the frequency and therefore energy decrease. At one end of the electromagnetic spectrum are radiations with long wavelengths, such as radio waves, that's used for AM and FM radio bands, cell phones, and TV signals. The wavelength for a typical AM radio wave can be as long as a football field. Microwaves have shorter wavelengths of higher frequencies than radio waves. Infrared radiation is responsible for the heat we feel from sunlight and the infrared lamps used to warm food in restaurants. When we change the volume of the TV station on the TV set, we use a remote control to send infrared impulses to the receiver in the TV. Wireless technology uses radiation with higher frequencies than infrared to connect to many electric devices, including mobile phones and cell phones and laptops. Visible lights with wavelengths from 700 to 400 nanometers is the only light that our eyes can detect. Red light has the longest wavelength of 700 nanometers, orange is about 600, green is 5, violet 4 has the shortest wavelength of visible light. We see objects of different colors because the colors reflect only certain wavelengths, which are absorbed by our eyes. The electromagnetic spectrum shows the arrangement of wavelengths or of electromagnetic radiation. The visible portion consists of wavelengths from 700 nanometers to 400 nanometers. Ultraviolet light has shorter wavelengths and higher frequencies than violet light or of a visible range. The UV radiation in sunlight can cause serious sunburn, which can lead to skin cancer. While some UV light from the sun is blocked by the ozone layer, the cosmetic industry has developed sunscreens to prevent the absorption of UV light by the skin. X-rays have shorter wavelengths than ultraviolet light, which means they have some of the highest frequencies. X-rays can pass through the soft substances, but not metal or bone, which allows us to see images of the bones and teeth in the body.